Hey y'all. My name is Amelia. This is Heat and Mass Transfer. Today we are doing Adventure 1A, or actually this is problem 1.063. So it's problem 63 in chapter 1. And here, if you can see my screen, we will be going over a few schematics that have been provided by the textbook in an outdoor setting. In which, with the case we consider of solar radiation on a semi-transparent medium, wherein the radiation is emitted or transmitted, or absorbed or transmitted depending on the wavelength. So the long wavelength will be absorbed by the medium, and the short wavelength will be transmitted by the medium if the medium is at least semi-transparent. It is requested that we look for all the cases provided, heat transfer processes to just define them, get a good idea of, this is what this schematic looks like. Here's all the relevant heat transfers processes associated with it. So we've got case A is single and double paned windows. Case B is a flat plate solar collector with and without a cover plate. Case C is a triangular solar collector, and case D is an evacuated tube solar collector. So for A, here we've got this schematic courtesy of Bergman and Levine 2017. We are assuming just a couple of assumptions here right off the bat. There's no radiation between the room slash the window and the outside surfaces because they didn't give us any kind of like external surroundings temperature. We're assuming that it's not like small body, large enclosure. We're just going to say we're going to ignore that case of radiation. So the only radiation that is being in this problem is coming from this radiation, the solar flux alpha G, which is represented by this squiggly arrow. Next, we can also assume that the inner pane here, or at least, the single pane or whichever pane here is going to be facing the room, that is small object, large enclosure with respect to the room walls. A few more assumptions. We're going to say the panes are identical, because if they weren't, we'd be having some problems. We're going to say the air gap between the panes poses no obstacle to radiation, so there may be some radiation depending between these two panes. We're going to assume that it doesn't pose significant obstacle. There's nothing we need to take account for. We're going to assume that the energy transmitted by the first pane for the radiation is also transmitted by the second pane, so there's no like energy changing wavelength. There's no weird losses that we'd have to deal with. We're also going to assume finally that the overall heat flow, because it did mention in the problem statement, which I should have noted here, that in this specific case, the ambient air is cooler than the room air. So this is kind of like in the winter when you're trying to keep a room warm. So due to that, oh, it is noted over here. We're going to say that the overall heat flow, we're just going to assume is from the room to the outside. So for the double pane case, we've got radiation incoming from this, this sun, and whatever is transmitted, the short wavelength, is just going to end up in the room air. Whatever is not is going to end up absorbed by this window panel here. And then we're going to also end up having some convection. So if we're here in the room, we're going to have some convection. You're going to have heat convect into this pane, and then it's going to conduct through that pane, and then it's going to convect and possibly radiate between these two panes, and then it's going to conduct again through this second pane, and then it'll convect out to the ambient air. So it is something that we don't know in terms of just the quantity of energy coming in here. And so it's likely not important yet in terms of concept, but in terms of mathematics, the signs could change depending on like how much energy is actually being received at this outer pane. For the single pane case, we're going to again have the same incident alpha G, incident solar flux onto the single pane window, but it's a lot easier. It's just going to conduct through the single pane window. Or sorry, first we're going to have so there's that incident. And then if you have, long wavelength gets absorbed, short wavelength gets transmitted, same deal. We're going to have this room air that's hot. It's going to convect into its heat into the single pane. The single pane is then going to conduct through it, and then it's going to convect to the outside. So that is all summarized here. Here's a flat plate solar collector. There was no image listed in the book, so here's one I pulled off of the Energy Information, or yeah, EIA, don't recall it, but yeah, U.S. Energy Information Administration. So you've got this solar collector, um, and it's basically just like a black box with some pipes in it, and a transparent case with or without the transparent case. And so here we're another one of our assumptions. We're going to assume that since the collector collects heat, because the point of this is you take all of this incident solar radiation, capture it, use it to heat up like pool water or something. So you get your warm jacuzzi. Um, Without the transparent cover plate, we're going to again input solar flux to the absorber plate. That's going to be, there's no squiggly line drawn in here, but that's the same alpha G as earlier. We're also going to have an output from this one. We're going to assume it's a small body and a large enclosure. So we will have possibly, depending on how nitpicky you want to be, some losses between the body of this collector and sort of the roof it's on and other stuff such like that. We also, in terms of convection, because we're assuming that the solar collector is going to be hotter than the ambient temperature, we're going to have some convective losses from the absorber plate to the air, but we're also going to have convective transfer into the fluid being heated. So if you've got all these pipes on the back of the solar collector, you've got that incoming energy, the radiative energy is going to get absorbed by the collector, and then it's going to conduct through whatever material it has to conduct through, like say a pipe wall, and then it's going to convect off into your fluid, and your fluid's going to be warm. So again, conduction through the absorber plate, conduction through the pipe walls. So that's all listed here. For the case with the cover plate, again, same input solar flux as usual, same long short split. In terms of convection, we're going to have, sorry, in terms of radiation, let's cover this real quick actually. The whatever short wavelengths pass through the cover plate and then will be absorbed by the absorber plate, because it's kind of like a sandwich, right? You got your like absorber plate and you got your cover plate here, and then you've got your incoming solar radiation. So with the convection here, we've got your convective losses that were covered earlier. Same thing of just, hey, this thing is warm, it's going to be losing energy somewhere. And also the fact that the whole point of this is to take that radiative energy and put it into convection, convect it into your water or whatever other fluid you choose to use. There's some weird ones out there with like acetone and stuff. Conduction. The energy input that is coming through that cover plate. So like if you're I'm not sure if you guys have covered this quite yet, but there might be contact resistance. Contact resistance is basically, if you haven't covered it yet, it's like if you've got, take your sandwich example, you got a ham sandwich, right? And on one side of your ham sandwich, you've got bread, and ham in the middle, and let's say you're trying to toast it. You're putting on a frying pan. You've got a heat source at the bottom. The heat is going through the bread. Actually, better example, grilled cheese. And you're trying to melt this cheese, right? But usually, when you're trying to melt this grilled cheese, initially it's really hard to melt it. Partially that's because the heat has to conduct through the bread, and bread is not like metal. It's not a great, heat conductor. And partially it's also just that you have this resistance because there's all of the bread is rough. If you zoomed in at the bread, it would not be a smooth surface. So there's all of these, it's kind of like friction in terms of when you're like, you guys have taken statics. In terms of like, the friction between all the little bumps on both objects, it's the same thing. If the objects are because of it's because of all those little, nibs and knobs, you're going to have a lot less efficient heat transfer between the two. So grilled cheese, it's kind of hard to get your cheese to initially melt. With this, so we're going to have that same thing potentially, and then it depends. You can also just assume that it's not there, and you can also, mitigate it with a lot of other things. So we can also, if you would like, we can just assume that contact resistance is negligible. But whatever energy input ends up, in that cover plate that was absorbed by the long wavelength that gets absorbed by that cover plate it has to go, oh, I'm in the cover plate. I don't want to be in the cover plate, and it is going to have to either convect away on whatever convective losses you have, or it's going to conduct through the absorber plate and into the pipes. So triangular solar collector, that's our next case. Here's our little schematic as usual. We're going to assume the styrofoam insulation is absolutely perfect. You didn't get this stuff at Home Depot. This is like the fancy, $100 ice cream cooler type stuff. It's also magical. We're also going to assume the system steady state, because that usually will make your life significantly easier. If you can assume it's steady state, assume it's steady state. Again, double pane semi-transparent cover. So we're going to have the same issue as earlier with the double pane window. We're going to have some wavelengths transmit through the panes. We're going to have some wavelengths of the radiation be absorbed by the outer pane. And we are going to have that air gap is going to, again, it's double pane, so you're gonna have those two panes that'll restrict the it'll just make it more complicated for the heat to get out. You've got your absorber plates, so again, short wavelength that goes straight through, just gets absorbed by the absorber plates. You're going to be blowing air through this. This is actually a side cut of a duct. So you're going to have all of this air flowing through it that's going to convect away all of the heat that is stored in your absorber plate. So and you're also might, again, depending on how warm this double pane cover is, might have some convective losses to the outside. But primarily, the goal of this is going to be, hey, we got a bunch of radiation. We're going to absorb it in the absorber plates. We're going to insulate it here to prevent any kind of conduction through this styrofoam. So we're going to make sure we don't have losses there. And then the air that you blow through this duct is going to be heated up by the air, or by the plates through that convection. Conduction, excuse me, sorry. Same thing in terms of if you get some, depending on, which direction all the heat flows, but you might have, since it's really hot air in here, depending on how warm this cover is, you might have some hot air in here that will convect into the first pane of the cover, conduct through that pane, convect and radiate to the next one, conduct, and then convect away. Last case, we have our evacuated tube solar collector. This is a similar idea, except you've just got a bunch of vacuum tubes or evacuated tubes, and then around them you've got this clear outer tube. Actually, here's a better diagram over here. It's all labeled for you. Very nice. Thanks, Bergman and Levine, 2017. And through here, very similar idea. You're just going to have all of this incident alpha G solar flux. And that is going to, again, short wavelength goes through the transparent cover and ends up in the space inside into the working fluid. Short or long wavelength gets caught by the transparent tube, and then it's another case of just, hey, actually, sorry, not by the working fluid, I misspoke. The short wavelength radiation will be caught by the opaque inner tube, because this inner tube is opaque. It's actually two tubes. So you've got your outer tube, which is transparent, and your inner tube, which is opaque. Following, you're going to, again, as usual, because the point of this is to heat up a working fluid, you're going to have your convection. It's going to be in the center here. It's going to take away all of the heat trapped in the inner tube away by convection. There's a reflecting panel here, so any radiation that misses will be able to make another pass. Depending on the environment you're in, you might also have some convective losses to the outside from the transparent outer cover. Additionally, conduction, again, between these two walls of tubes, you're going to have some heat. So for example, in the inner part of the tube, partially you're just going to have some heat that's going to have to convect through the wall of that tube. Partially also whatever long wavelength gets caught by the outer tube might, again, depending on the way the situation is set up, might either just be lost to convection or might get directed inwards and conduct through the tube walls. So that is it for 1.063. Thank you. for thank you for coming to my TED Talk. Yeah. All right. Bye.